In this video, I'm going to solve the following problem on inventory control. So a company manufactures hospital supplies and has uniform demand of 170,000 boxes of bandages per year. Actually, let me copy some of this data over here. So it's 170,000 boxes per year. It costs $10 to store. Again, these storage costs are proportional to the time stored. So if we store a box for half a year, it costs $5. It costs $185 to set up production. And it costs $1.50 to manufacture. And the question is, how many production runs per year should the company do to minimize their cost of production? And the trade-off here is that the more times we produce the bandages, the more times we have to pay this $185, but the less time we actually have to store the bandages. So there's going to be a trade-off here between storage cost and production cost. All right, the general strategy for these types of problems is to, one, choose a variable, or variables, but variable in this case, determine the total cost of production using this variable, and then use calculus to find the minimum cost. Okay, so choosing a variable, if I think about this, there are two related variables. We're going to choose one of them. The first variable that we could choose would be the number of production runs, call that n, or we could choose the number of boxes we want to produce per production run. Now, to me, the natural choice, given that we're trying to figure out how many production runs we want to do, I would choose the number of production runs. But both of these will work and we should get the same answer. Okay, so total cost. So we want to figure out the total cost, and we're going to split this total cost into two parts. There's going to be the production cost and the storage cost. So let's look at the production cost first. Production cost. Okay, so let's call that cost of production. Well, I want to think about the cost of production per time I set up my production, right? So I'm going to divide my year, I'm going to divide my boxes, and do a certain amount of production each time. So we're going to do this n times, and it's going to cost us $185 each time we set up production. And each time we set up production, we're going to produce 170,000 divided by n boxes. And each one of those boxes costs $1.50. So if I multiply this out, it's 185 times n, and 170,000 times 1.5 is 255,000, so it should be plus 255,000. So that's my cost of production. And then we have our storage. Storage is a little harder. So cost of storage, again, we're going to multiply by n. Now we have to think a little bit. Each time we produce, we're going to produce 170,000 over n boxes. Each production run lasts 1 over n years. And each box in the production run lasts for half of the period. So why is that? So imagine we produced all the boxes in one production run, then some of those boxes would be used almost immediately and not spend any time in storage, whereas some of those boxes would spend almost the entire year in storage. And so on average, if we average those boxes out, on average, the boxes would spend half a year in storage. If we did 2 production runs, then on average, the boxes would spend a quarter of a year in production, in storage, and so on. So this is how long does the production run, or do the boxes we produced at a particular time last, and then on average, they spend half that time in storage. Oop, and we forgot one very important thing. Costs $10 to store our box. Okay, so this is the n stays, so we've got 10 divided by 2, which is 5. 5 times 170,000 is 850,000 divided by n. So my total cost, bring it over here, is 185n plus 225,000 plus 850 over n. So now we've got our cost equation, and now what we want to do is minimize cost, and so this is where our calculus comes in. So we take the derivative. C prime is 185 minus 850,000 over n squared. We need to find a critical number, so we set this to 0. 0 equals 185 minus 850,000 over n squared. Multiply everything by n squared, and we get 0 equals 185 n squared minus 850,000. So n equals the square root of 850,000 divided by 185, which is 850,000 divided by 185 equals, and second square root, 67.78. 67.78. So that's our candidate, that's our critical number, and we need to just check whether or not the second derivative is positive or negative. We're going to check convexity. So the second derivative of this function is 2. We've got a negative sign. We're multiplying by -2, so we get 2 times 850,000 over n cubed. If we plug in a positive number into that, then c double prime, second derivative at 67.78 is certainly bigger than 0. Convex up means we have a minimum. So costs are minimized when we have 67.78 production runs per year. And most likely, of course, we would round that to probably 68 production runs per year. We wouldn't can't run 0.78 production runs a year. Although, to be fair, that just simply means a 0.78 production runs per year just means that if we started production runs on January 1st, the final production run, or the production runs next year, would start on some other day. So 67.78 is a reasonable answer to this question. And that's it. That's how we solved an inventory control problem.